Do you guys want to do an example from 4.9, or do you want to? You guys like? Eh. All right, let's see. I don't remember what I assigned, but it doesn't matter. Let's see. Anyways, look at number. Let's see. Number 11 looks interesting. Kind of nice. So did they give you? Yes. Okay. Cool. We should do this one now. Okay. I want you to know something. If you get rid of x and you solve for y, it's kind of the bad way to go. If I get rid of y and solve for x, then this first equation I can have y equals. So you sort of look for that so you see which one to solve for first. You can't always do that. Like number 15 is, you can still do it, but number 15 would be really gross. Number 15 is one where you almost want to go ahead and kill twice. You know what I mean? I know I teach very violent mathematics, but I won't. So I mean, what would I do first here if I wanted to kill the y so I can get x? All right. Operate.
Oh yeah.
There you go. Whatever, man. So operate on this with b. So I get. Yeah, d cubed minus d x minus dy equals 0, so then I can combine these. You guys see what happens here? Yeah, you get d cubed minus 1 x equals 0. You guys see that? Is that cool? Everybody see that?
How did you get
I don't know. How did this happen?
or like what were you saying?
Yeah, so if I add these together, I'll get d cubed, this is dx minus dx, minus 1x, so that's d cubed minus 1x, yeah. These die equals 0. All right, correct? And then from here, what do I do? So the auxiliary is basically staring me in the face, right? M cubed minus 1 equals 0. Don't do m cubed equals 1, m equals 1, or something weird. How do you officially solve this? You guys remember, by the way, you guys have done this. Have you guys done this? Where the real answer is 1. The other two answers have to be, have to split this up into 3 parts. I don't know if you guys have ever done this before. So 120 degrees, 120 degrees, 120 degrees. Does that sound familiar to anybody? Where you get to complex answers? So this is the complex plane? All right, I always forget where you
Did
do
you
that.
talk about it before?
No. Maybe I did a little bit about the rotation thing or something. Yeah. But this takes that even one step further, and this is the whole idea of rewriting complex numbers in like, there's a few different ways you could do it. R, e to the theta kind of thing, or e to the I theta. Stuff like that. But anyway. So you're always going to get a real answer and then 2 complex answers that are 120 degrees away from that. So what's the math 90 way of doing this? Well, because that's like the math 300 level maybe. How do I do cubes? Little dude, big dude? 1m, yeah, minus 1, 1, 2 m's, 1 squared is 1. And I just taught this today in my Math 90, and I told them, you know, this is like Pulp Fiction. This is the cleanup dude. This is the wolf. If you've never seen Pulp Fiction, then go see it. But this is the guy that kills the shit you don't want. It's always this times this. Here I get m equals 1. Here I have to use, what do I have to use? Quadratic. So I get negative b plus or minus square root of 1 squared minus 4, so I get negative 3 there. Is that right? So I get negative 1 plus or minus, let's see, negative 1/2 plus or minus I rad 3 over 2. And then, so what does that lead to for answers? X equals
C1 e to the x.
yeah, C1 e to the
X. Oh, it's t.
t. So for these, we assume that x and y are both functions of t. So big D means d by dt. E to the t, and then these, what would happen with these?
Plus e to the negative 1/2 t
Yeah,
times C1 cosine.
yeah, C1 cosine, rad 3 over 2t plus C2 sine, rad 3 over 2t. Cool. That should be old news. This is just constant coefficients dE. I can do that with auxiliary equation, assuming an answer of the form e to the mt. And since now I know x, y equals d squared minus 1. Right? So I would take two derivatives of this, and then take that second derivative and subtract this from it. Right? And that way, if I do that, I avoid having to do the whole balancing the constant stuff and doing like C3, C4. Right? So you can do it either way. This is a situation where it's definitely easier to solve for one, plug it back in, and get the other one. But like I said, there are situations where that's not advisable, possibly. Yes?
Shouldn't the C's be 1, 2, and 3?
Yeah, thank you.
I just
You're good. C1, C2, C3. So I mean, so to finish this up, I know that y equals d squared minus 1x. So now I just throw this in here. And I get the answer. I take the second derivative of it, and I subtract the original from it. It'll be nice like terms, because after the second derivative, these will line back up with each other. Right? And this will just be constant times this, and this will be itself still. All right, is that all right? No, yes, no? Okay. Okay, I just you got to get in there and try some of them out, so you got some specific questions about them. Okay. So 5.1 is extra credit. You can still ask questions about it if you try it out. We're going to get into chapter 6. Chapter 6, I don't know how long it's been since you last took, since you took 280. And normally everybody's favorite part of 280 is series. So that's exactly what this section is all about, is sometimes the answers to, I like that reaction. Sometimes the answers to differential equations are power series, and that's it. And sometimes those power series actually relate to a function, and sometimes they just don't. Sometimes you're just open-ended. There's no closed kind of form for them. Right? So, I don't know. If you look on page, just to see if this jogs your memory. In fact, let's do this. Let's do this real quick, since I was going to do it earlier this semester. Might as well do it now. Page, what was it? Page 234. Get it like that. Page 234. It tells you that e to the x is is 1 plus x over 1 factorial plus x squared over 2 factorial, right? And this is where we start using summation notation to write this a little bit better. I don't know if you guys remember, how would you develop this? What is this called, this thing here? This here is called what? Yeah, it's a Taylor series. It's Maclaurin because it's built around 0. So in general, it could be x minus a if you want to build it around some other point. The general term is Taylor series. And Maclaurin series is if it's built around 0. Does this jog any memories? Or have you buried them deep in the recesses of your brain? All right, no? And so this is the Taylor series, the Taylor polynomial. If I want to write the Taylor series, I can use the summation symbol, right? N equals to infinity, x to the n over n factorial. I think they put that in there. Yeah, cool. Okay, so hopefully this looks familiar, possibly. So let me put 2 more up here. I love cosine and sine, and you'll start to see why it would be expected for there to be some kind of relationship between these. So cosine is this guy. X to the 2n, something, yeah. There you go. I like it. And sine is kind of like the missing terms. It's kind of nifty. Right? So like, what's this one missing? It's missing an x term. It's missing an x cubed term. Right? So sine x starts at x. And I don't know if you guys remember. You guys know the, well, this is the linear approximation for sine. Or if you take it in any physics, sine theta for very small theta is theta. What's sine of 0? 0. So if you're really close to 0, what's sine of 0.0003 radians is 0.0003. It's a good approximation. If you don't believe me, put it in your calculator, right? So hopefully this sounds familiar to somebody out there. This is a very often used thing in physics. You should have done some of this linear approximation stuff back in 180, 280. So this has got x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And then it keeps going. Did they show you the whole thing? Oh, then they give you blah, blah, blah. Cool. All right. So, something to realize is if I wanted e to the x squared, the beauty of this is just like a function. This is just the f of x. So f of x is equal to x, which is this. F of x squared is e to the x squared, which is 1 plus x squared over 1 factorial plus x to the 4th over 2 factorial plus. Do you guys see what I'm saying? That's the beauty of, it's another part of the beauty of this is if I don't want x, I want x squared or something, I just replace all the x's here with x squares. And it's the valid, actual Taylor representation. So what would e to the ix be? If e to the x is this, what's e to the ix? 1 plus ix over 1 factorial, right? What's ix squared? Negative x squared. Let's do a few more here. This would be, just to get a few more in here, plus x cubed over 3 factorial plus x 4 factorial. So this would be plus, now actually, what is ix cubed? Oh shit. What's I cubed? Well, if I squared is negative 1, I cubed is times 1 more I cubed is negative I. And then what's I to the 4th? Ix to the 4th What's I to the fourth? 1. That's the cycle, right? Every fourth one, it becomes 1 again. And just remember, I is just a half rotation. So one rotation is I, another rotation is -1, so that's I squared. Another rotation is -I, so that's I cubed. Another rotation, I to the fourth, is 1 again. Hey, shit, and then it does the whole thing again, yay. So where am I? Blah, blah, blah. So this would be plus, where am I? X to the fourth over 4. Because I to the fourth is 1. Dot, dot, dot. Now watch. What's that?
Cos.
Yeah, it's cosine. Oops, yeah. And then what's this? It looks like I times sine. So e to the ix equals cosine x plus I sine x. Therefore, e to the I pi is cosine pi plus I sine pi. Well, what's sine pi? 0. What's cosine pi? -1. So e to the I pi plus 1 equals frickin' 0, which is that thing on my shirt. Oh my God, we made it! Yay! What really sucks for you guys is there's just not enough time, or we don't put enough history in. And so on that note, I want to give this to you. Do not fry a synapse looking at this. I am not saying that you are going to have to be able to do this. I just want you to see this. Derivatives were invented after people were playing around with summation stuff, right? The history is so different from the way we teach it, which kind of makes sense. We make a lot of shit up and then we go, well, how do we want to teach people this? We don't want to take them through all the freaking weirdness that we had to go through. Let's figure out a progression. So we teach things, some of the stuff we teach is completely backwards. And you just don't even know it because you never learned the history of it. But this is one little, before I do this. So look at this here. Sum n equals 1 to infinity. 1 over n squared. Who remembers this one is? I'm going to work with this one, but anyone remember what this one is? Harmonic series. Does this sound familiar to anybody? Does the harmonic series converge or diverge? Diverges. I like it. So this infinite sum does not equal anything. This one converges. You never find out what it converges to. It converges to pi squared over 6, of course. What? So let's check it out. N equals 1. It starts at 1, I think, yeah? Yeah, Jeff. N equals 1 would be 1, right? Is that cool? N equals 2 would be 1/4. N equals 3 would be 1/9. N equals 4 would be 1/16. And then let's do a couple more. Somebody help me out. Add those up. It should be decently far out to compare. Do you guys see what I'm about to do? I'm going decently far out, and then I'm going to compare it to what this says in my calculator. If that is this, then after this many, it should be getting pretty close. At least to like the 4th decimal place or something, possibly. Maybe 3rd. We'll see. I don't know if you guys are really with me or not. Please tell me this. Everybody in here should be comfortable with this symbol. That's part of the prereq for this course, and that's why you go through 280. So 280, I know you go through hell with the series. I don't know why students hate it as much as they do. I really honestly don't. But they do, normally. But this symbol by itself is not an evil symbol. It's actually really easy. Just plug in 1 in, and then 2 in, and then 3 in, and then, of course, we do weird shit with it after that, but too bad. So what do we get here? 1 plus, what are you guys getting? 1.4913, yeah, sure, okay, I like it. Now try to do pi squared divided by 6. That's getting close. Maybe they added some more. If I add some more terms here, let's add 149, 164th. Let's see. If I add in 149, 164th, you get 1.52, and then I add in 181st, and then I add in 100th, 1.54. Do you guys see? If I keep on going, it's going to approach the actual answer at 1 point. Where did it go? 644. Blah 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 blah. Keep on adding. 100th is 0.01, so I'm going to be off in the. After that, I'm going to be off. 100th is going to keep adding in that second decimal place, so it's eventually going to catch up. All right, maybe. Now, so let me give you this. Again, you are not expected to be able to do this kind of thing on your own. Freaking Euler, who many people think was an alien. Not many. How does he know? He had a lot of free time. Okay, one more. The exceptionally freaky thing, let's see. Well, it's nothing too freaky. All right. So I'll let you guys peruse that. So you can, the interesting thing is what you can do with these infinite sums. Sine x over x would be 1 minus x squared over blah, blah, blah. You just divide everything by x. So that is allowable, right? Of course it is. Because this is just a statement of fact, so whatever I do to this side, I do to that side, and the equality holds. Now, of course, each of these, the ones I've got up here, they all have intervals of convergence from negative infinity to infinity. Who remembers the phrase interval of convergence? I mean, if you took 280, it's got to be something you almost can't escape in your dreams, right? Okay. All right. Anyway, I'll let it go. There's just a lot of nifty history that I just wish you guys got. And as a student, I didn't even know what I was missing out on until later. You get a math degree, and then you start looking into some stuff, and you start seeing the history, and you're like, why did I never learn about this? There's just no time. Oh, man, the history of math, it's got duels, it's got poisonings, it's got... Oh, dude. It's crazy. It's almost as neat as Helvetica. No? Okay. All right. So we go where they went from this. This is, again, on page 234 in the book. Some of these functions that have Taylor series representations. Okay. So let's dial it back in. I just want to give you guys a crash course to see if I can't restart some of those old memories. I'm going to go ahead and give you this here. This is an old 280 handout that I kind of beefed up a little bit for you guys. it to? Yes. So, I mean, some of the first stuff should be real review kind of stuff. The general way to write power series is this way. And this, of course, defines a function of x. And like any function, it might have a domain that's restricted. So there are certain functions, there are certain power series that only work for certain values of x. So right in the middle of the page, it talks about the three situations that might happen. This would be, like Darren said, this would be a Maclaurin series. Because it's been expanded around x minus 0. So it works best near 0. It works perfectly at 0. If I do this guy, got it. That's going to be your Taylor, not Taylor series. There's going to be a power series centered at A. Whatever you choose for A. I like it. Now, the difference between pure power series and Taylor series is, I don't know if you guys remember how to construct a Taylor series, but you basically had to take, you're given a function and it says make a Taylor series out of this. So you do a lot of derivatives. And you have a form for Cn to plug into, right? So that's how you construct a Taylor series. So Taylor series, you start with a function and you construct the series. Differential equation solutions, we get a power series answer that might be a known function. Or it might just be an infinite series of shit that doesn't really come down to any function that we know. All right. Of course, the second situation being the less satisfying, but oh well, it's too bad. Okay, I like it. So three things can happen. Either it only works for A. Right? Either A is the only thing it'll work for, because if it's not A, these things just blow up to infinity no matter what. Or it works for some interval around A. Or it works for everything. So those are the three things that could happen. It only works for A, it works for some finite interval around A, or it works for everything. So those are the only three things that can happen. And the nice thing is it's always centered at A. So you have this idea of a radius of convergence. And then you have an interval of convergence. Which would be A minus R, A plus R. So R could be 0, in which case this is not an interval, it's just a point. It only works for A. R could be some finite number. So that's a true interval. Or R could be infinity. So that would just be negative infinity to infinity. Like it. One of the do you guys, I keep asking if you remember stuff. If you don't, you probably should go review. But do you remember like root test and alternating series test, integral test even? The one we normally use would be ratio test. That's the one that normally comes up with power series solutions to differential equations, is the ratio test. And that's why I focus on ratio test on this handout. Right? Blah, 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 blah. I gotta put something in there about absolute convergence just because. So let's try some of this out. Let's see. Let's see if you guys remember how this works. Let's do one of these together, and then I'll have you guys do the rest of them alone. Let's do the first one, the easiest one together, because that's what teachers do. This is the very bottom of the page. I want to find the radius of convergence. First off, what would Cn be in this? Comparing it to the general form, what is Cn? What are the coefficients? What's the general form for a power series? let's say you're centered at 0, so this would be some Cn x to the n, right?
Over n factorial.
Yeah, so Cn is 1 over n factorial. Now everybody in here knows what factorial means, right? If you don't feel bad. It's not necessarily struck on you, but just to make sure everybody remembers, how would you do 7 factorial? If I made you do it by hand, you'd have to do 7 times 6 and 5 and 4 and 3 times 3. And if you're curious, you should look up for non-integer interpretation of factorial. If you think about that for a second, your head might explode. But there is actually a definition for like 1/2 factorial or negative factorial. Yeah. If you don't believe me, just Google it. I like it. Okay. So here, how would I apply the ratio test? So the ratio test says, take the limit as n goes to infinity of the ratio of the next term divided by the previous term. All right, so the term with an n plus 1 in it divided by the term with an n in it. The limit as n goes to infinity of this stuff with an n plus 1 in it and what I normally do when there's a fraction here is when you divide, of course, you multiply by the reciprocal. So times this stuff with an n in it, which is what this stuff is, the reciprocal. Okay, this is a good review to remember how factorials work with n expressions in there. What can I do with that stuff in there? Anything I can do?
Cancel out everything but like n plus 1 on the bottom. The ends.
Yeah, how does the n factorial cancel? You can't just cancel the punctuation, right? And I know that's not what you mean, but how would I write this out so I could see it a little better? Well, what's x to the n plus 1? It's x to the n times x. I like it. So you can see the x to the n's. If this was 7, it'd be 7 times 6 times 5, but wait a minute. It'd be n plus 1 times n, yeah, times n times, but stop, because then these die. I like it. So does that feel familiar? Okay. Some of you guys are like, I thought I got away from this shit. So I get x over n plus 1. And what's the limit as n goes to infinity of that? No matter what the value of x is, that's going to 0. The bottom goes to infinity, the top is some finite choice for x. So this is going to go to 0. And how do I interpret the results?
What's the variable? What's the variable?
Yeah, if L is less than 1, well, I forgot my little absolute value right here, it doesn't really matter because it goes to 0. If L is less than 1, then that's going to converge. Right? And does it depend on the value of x? If x stays around, then that's going to determine the smaller interval of convergence. But here, does it depend on the value of x? Does any value of x make this not work? No. So then what's my interval of convergence? Negative infinity to infinity. So what's my radius? Infinite radius. Infinite r. The interval would be negative infinity to infinity. Because there is no x dependence. So you guys try the second one there with the square root in it. What's this limit? 1, yeah. Right, be 1 plus 1 over n over 1 goes to 1. Is that cool? If you remember, just remember, inside here is just a ratio of polynomials, right? And if the degree is the same, the limit's going to be the ratio of the coefficients of the highest degree term, which is 1. Good old horizontal asymptotes, right? I like it. So that's 1. And what do I want to force? So the result is the absolute value of x. Now, in order for this to converge, the result has to be less than 1. And real quick, who remembers, would this converge the series? Will this converge? Will it converge? This is a geometric series where the inside is greater than 1, so the limit's not even 0, right? I mean, in order for a series to have a chance to converge, the limit of the terms has to be 0. Now, when I say that to my 280 students, they hear me say the opposite. If the limit is 0, then it converges. I did not say that, right? It's basic logic. If the limit of this is not 0, then it is divergent. If it converges, then the limit of this is 0, right? Well, this guy, the limit is not 0, so it's screwed. Anybody remember this is called a, what kind of series? Anybody remember? Has an R geometric series? No? Nobody? All right. So R equals 3/2, which is greater than 1. All right.
Remember, I just don't remember all of
This, I really want you to understand, the ratio test is looking at a series as if it has an R that's not constant. If that R eventually gets below 1, then it's going to converge. If it never gets below 1, it's like this, it's not going to converge. That's why the ratio test works the way it does. Cool? Yeah, exactly. When you first realize that, now some of you guys don't even remember geometric, and I don't blame you. It's been a while, or you just had a rough experience in 280, like blot it all out. But it's a bad idea. It's a pre-art for a reason. So that's the interval of convergence then, from -1. Now at the endpoints, I have to check it out. I don't know if you guys remember this. There's no guarantee at the endpoints is where it's equal to 1. So if I put -1 in here, it would be alternating series, but the square root of n, does that go to 0? I don't know if you guys remember. Maybe I don't have to get that deep into it. So I have to check the endpoints, because I don't know currently if the endpoints converge or not. So if I put x equal to -1 in, what does the summation, what does the series look like now? -1 square root of n, right? Alternating series. Alternating series says as long as this goes to 0, the whole thing converges. Does this go to 0 as n goes to infinity? Does square root of n go to 0 as n goes to infinity? No! It goes bigger and bigger. And then x equal to 1 will be even worse. It's got no chance. It's not even alternating then. At least the alternating was killing part of itself. Right? Remember alternating? 1 minus a half, plus a fourth, minus, it's like, whoa, it's killing parts of itself. It has a chance to converge, right? All right. So this is going to be the interval of convergence. So the radius would be 1. Okay, guys, look excited. Try out the third one. I like the third one. It's got a lot going on.
Just 280 or 280.
Yeah. Nothing new yet. The new thing is on the back. We're eventually making it there. And the new thing is a lot of new shit with it. So yeah. So you don't make it a big deal when you take the absolute value, the negative 1 to the n, just forget about it, right? Dies. It's the absolute value. So. Absolute value makes it always positive. Yeah, so that piece, that alternating piece, goes away. So we're left with in here x. 3, and then we got n plus 1 over n plus 2. Of course, this limit, again, yeah, is 1. So I get x over 3 is the result, and the result, I force it to be less than 1 so that it'll converge. You with me? Whatever the result is, it's got to be less than 1. So we're trying to figure out what values of x make that happen. So I've just effectively made a statement. If I solve it, I see the values of x that make the result less than 1.
It'd be different if that x was an n, then, right?
Well, if it was an n, it would have been taken care of here. Yeah, if I had like an n left over, then it would go to infinity, then only 0 would make it converge. Because if x is 0, then of course the whole damn thing is 0. That would be the only way. That would be an example where there's only one number. It would be a 0 radius of convergence. It's called the trivial solution. Right? So here, absolute value of x has to be less than 3. So it'd be from negative 3 to 3. And again, I have to figure out when I plug a 3 in what happens. Now this is kind of interesting. Let's take a look. I always got to check the endpoints to see what's happening there, because this doesn't say anything about those. It's inconclusive at those points. If x is negative 3, I get negative 1 to the n times negative 3 to the n, which is 3 to the n, divided by 3 to the n, so I just get 1 over n plus 1. Do you guys, is that cool? No? All right. So we put it all in there. So here's negative 1 to the n. So I get n negative 1s. X is negative 3. I have n negative 3s. So n negative 1s and n negative 3s make n 3s, right?
Well, yeah.
You just multiply these together, put an n on the outside, undistribute the power, whatever way you want to look at it. So that becomes 3 to the n divided by 3 to the n. Those cancel. So you got 1 over n plus 1. This is effectively what series? Yeah, it's harmonic. And harmonic diverges. So divergence. So I can't include negative 3, but what happens at positive 3? So this is if x is negative 3. What if x is 3? Doing this only tells you within. The endpoints, I don't know shit. L equals 1, it's inconclusive. So I have to check the endpoints individually. I don't know if this sounds familiar. Dredge up those 280 memories. Do you notice if x equals 3, I'm not going to lose the alternating piece. That's what's going to save this guy's ass. Sum equals 0 to infinity, negative 1 to the n, 3 to the n, over 3 to the n, n plus 1. So these kill each other. Leaving this alternating series test says you just need this piece to go to 0, and it does. So it converges, so therefore that's the interval of convergence. It still has a radius of 3, because any individual point actually has no length. Oh, you guys love it. Okay. Sorry. I was just thinking, it's like if you like chocolate and somebody put peanut butter and you hate peanut butter, you're like, would you just mess up my chocolate? But some guys don't like this course in the first place. And now I'm bringing stuff back in that you hated from some other course. You're like, it's like injecting liver with whatever you don't like otherwise. Injecting liver with Brussels sprouts or something. What have you done? Sorry. All right. And then the fourth one is interesting, but I want to get to the back here. I'll let you look at the fourth one if you want to. So here's the new stuff, the semi-new stuff. And let me see, before you even kind of look at that, let me just write this down here. Now this is just an infinite sum. This is, just an infinite, I know. But it's just a sum. Who cares that it doesn't end? I'm going to take a derivative of a bunch of things that are being added. That's awesome, right? So I want to remind you of this fact. So what happens when I take this guy's derivative then? What happens to the inside? This is just a bunch of constants, right? So they come for the ride. What happens to this guy? Yeah, n times x to the n minus 1. Now, one other thing happens that you might not immediately realize. It's not bad if you don't do this. It's just unnecessary. If you put n equals 0 to infinity, why is that unnecessary? Why do I not have to start at 0? Because what does n equals 0 lead to? 0. So that's why you'll see in the book they start at 1. There isn't anything magic about that. They just said, if n is 0, I get 0. Why the shit would I include that? So that explains why that kind of shifts backwards. Yes, sir?
N has to be integers. N is integers.
Yeah, and this, remember, that's what summation series are built on is, and we use the letter n because it's natural numbers. And actually we include 0 too, so it's like whole numbers, yeah. I like it. So yeah, n can't be some fractional thing or some irrational thing. That would be freaky. All right, maybe. And then you can just take another derivative and another derivative. So what does this lead to? Well, it leads to, at least for now, just like every introductory section has been, just about, is verification problems, right? Verify, so that's what I've given you here. Verify. Now, this is going to run into some issues, so I'm going to kind of let you do a step at a time. Verify that y equals the sum. Everybody with me on the back? N equals 0 to infinity. Negative 1 to the n, x to the 2n. Solves 1 plus x squared, y prime plus 2xy 0. Now, is this a form that we've ever looked at before? No, right? This is not a form. This is an example of unrestricted differential equation, right? Everything's been so